Okay, good morning, everyone. Today we are going to look at examples for Thevenin and Norton circuit. Again, very important topic, 30-point problem on the final exam, not by itself, because it's going to combine a lot of the topics from chapters 1 and 2 together in one single problem. Okay, so let's begin with Thevenin resistance. So this was the example. This was the example which has, again, I don't have any values in here. This is just the first illustration, first example. So it has four resistors, and we are asked to find the Thevenin equivalent resistance, RTH, between terminals A and B. Okay, between terminals A and B. Now, first step is to identify the terminals of analysis. In this case, the problem statement outright states find RTH between A and B. So you do not have to make any modification to the circuit. Okay, you do not have to make any modifications to the circuit. You simply begin your analysis. Okay, you do not have to take out any component. We are simply looking into the circuit from the perspective of these terminals and analyze the rest of it. So to find RTH, what do we do? RTH is a question mark. We reduce all independent sources to 0. And reducing all independent sources to 0 means replacing a voltage source with a short circuit and a current source with an open circuit. We have to eliminate all the sources that are present in the circuit, without which we cannot determine the Thevenin resistance. Right? So we eliminate all of those. Voltage sources are replaced with an open circuit. Current sources with voltage sources replaced with a short circuit, and current sources with an open circuit. Then we redraw the circuit diagram. Once we redraw the circuit diagram, we can see, let's start here. R1, R3, R2. That's V1 replaced with a short. This is where V1 used to be. This is where V2 used to be. Now note that I'm marking by 2 dots right here where the voltage source was connected. You don't have to do this. You can just simply draw a straight line. Okay. And then, of course, the current source was connected here. This was I2. This is A and B. Then we had another current source coming down here. And again, I am drawing this branch just to indicate the place where I1 was connected. You don't have to draw these two lines. Okay, you can simply eliminate it. R3 and R4. Wherever you see a voltage source, you place a short. Wherever you see a current source, you take it out. So you redraw the circuit. And I'll redraw it one more time. This is how it will actually look. A and B. So a 10-second pause while you write it down and let me know if you have any questions. 1, 2, 3, 4 resistors accounted for. 1, 2, 3 voltage sources and 2 current sources. Everything accounted for. Make sense? Is the application of the concept clear? Right? The concept is to find RTH. The concept is we have to reduce all independent sources to zero. Reducing a source to zero means replacing a voltage source with a short circuit and a current source with an open circuit. You redraw the original circuit diagram by applying this concept. And then if you have a reducible circuit, you reduce the entire circuit of resistors down to one single resistor from the perspective of the terminals of analysis, which is AB. All right, any questions? Okay, so let's look at what REQ would be between A and B. This time you're starting from the right side of the circuit. Typically we start from the left, right? So if your terminals, doesn't matter where your terminals are drawn, up, down, left, right, you always start at the farthest end. Remember the beginning of chapter 2? You always start at the farthest end from your terminals of analysis. So at the farthest end, we have R1. And we start reducing as we move towards A and B. So from R1, we have R2. What can we say about R1 and R2? They're in parallel. Once they are in parallel, we reduce it to one single resistor. So R1 parallel R2. Let's, R1 is in parallel with R2. Then next resistor up is R3. Series or parallel? It is indeed in series. And then finally, we have R1 in parallel. That entire combination of R1, R2, and R3 is in parallel with R1. And now you have your REQ or RTH, Thevenin resistance. Yes. Oh, yeah, it is R4. Thank you. R4, R4. Thank you. R1 parallel R2 plus R3, all in parallel with R4. You can apply the other technique which I had shown in class. We have A and B, and you just redraw the circuit resistors going from A to B. So we'd have R4. Then we'd have R3 connected to A. And from R3, we have R1. We also have R2. And then R1 and R2 are connected together, which is connected to B. Remember this technique, right? So here we can see quite clearly R1 is parallel with R2, which would then be in series with R3. And this entire branch is in parallel with R4 between A and B. And so RTH, Thevenin resistance for this circuit, is given by this equation. Again, there are no values here, but the point is that if the circuit is reducible, then you apply series parallel analysis and reduce it down to one single resistance. And that is your Thevenin resistance for that circuit. Okay. All right. Any questions? Any questions at all? So keep in mind that all circuits are not reducible. Okay. all circuits are not reducible, especially the circuits that we deal with in everyday life are very complex. They are not always reducible just because of the numerous connections that we have in there and numerous components and the way they are connected. Okay. They are neither in series nor in parallel. If I was to make one tiny change in the connection here, that resistor would not be connected in series or parallel, and you would not be able to find Req. So in that case, we have to find the Thevenin voltage and the Norton current and apply Ohm's law to find the Thevenin resistance. Again, important point from last week was why do we need to, why do we need to learn the technique to find all three quantities? Is for that specific reason. Sometimes you might have a dependent source in there. We cannot reduce a dependent source to zero. We can only reduce independent sources to zero. Dependent sources, the one with the symbol of a diamond, they cannot be reduced to zero. So in that case, again, we find Thevenin voltage and Norton current and apply Ohm's law to find Thevenin resistance. All right. Let's take a pause. Let me know if anyone has any final questions. Any questions? Okay, then let's move to a full-fledged example of a circuit. And our task is to find the Thevenin and Norton equivalent circuits for this circuit if, and this is very important, if the 2 ohm resistor is the load. Okay. In the previous example, the terminals of analysis were already given to us. So we did not have to remove that load or the second circuit. In this case, the problem statement states that the 2 ohm resistor is the load or the follow-on circuit. And so when you read that sentence, you have to remove that component from that circuit before you begin your analysis. That component should not be part of your analysis. Okay. And I'm going to go back a few slides where I had the summary written up. And that's the first point I had. If the question states, analyze from the perspective of a specific component, then that specific component should not be part of your analysis for any of those three circuits. Okay, so it goes back to this first point. Nope. So the 2 ohm resistor should not be part of your analysis. The terminals are named A and B. We'll stick with that convention. But again, if it's not given, you can remove that component and your original circuit looks like this. A and B. This is 12 ohms, 4 ohms, 6 ohms, and a 30-volt source. Now you analyze the entire circuit 3 times from the perspective of the terminals A and B. So when you begin your solution for a quiz or for the exam, the first step is to set up the problem correctly. And in setting up the problem, this is the absolute first step. That's the absolute first step. 2 ohm resistor is considered a load, so it's not part of, or it's not considered. It's stated as the load, and so it's not part of our analysis. Now we redraw the circuit 3 times. Resistance, voltage, and for current. Take it one step at a time. Let's tackle resistance first, RTH. For RTH, we reduce all independent sources to 0 and then find the REQ between our terminals of analysis. In this case, we have a voltage source. So I'm going to short out that voltage source. Or not short out the voltage source. Incorrect. Poor choice of words. I'm going to short out the circuit where the voltage source was connected. I remove the voltage source and replace it with a short circuit. 12 and 4 and AB. And our task is to find REQ between those terminals. Straightforward, considering everything. I have 12 in parallel with 6 plus 4. 12 in parallel with 6 is 72 divided by 18 plus 4. That should give me 12 times 6, 72. 72 divided by 18, 4, 8 ohms. Yep, 8 ohms. The resistance is 8 ohms. I don't know why I'm writing with red ink. Let's do black. Yes. Yes, it simply stated find the resistance between terminals A and B. So we did not remove. So the question being asked is, in this example, we did not remove R4 specifically because it simply said determine the Thevenin resistance between A and B. So then no modification needs to be made. Whereas in this example, it states that the 2 ohm resistor is the load. So we remove it. All right, any questions? Yes. I'll move it back, maybe Sunday. It has superposition only had 2 problems. This one has more. So maybe Sunday. Okay, any questions? Easy enough. All right, VOC. VTH, Thevenin voltage. Once we find the values for RTH and the circuit diagram, we forget this, okay? It is no longer part of our analysis. Again, we go back to the original circuit, and now we're analyzing the original circuit to find Thevenin voltage. If we use this circuit, there is no source in that circuit. So there is no voltage or current present in the circuit. And RTH, the value of RTH has no bearing on determining or the analysis for VOC and ISC, okay? So VTH, we are going to go back to our original circuit without the 2 ohm load. So this is 30 volts. VOC, 12 ohms, 4 ohms, 6 ohms. I particularly like this circuit. It's a very simple circuit, but it's a very important concept of electrical engineering. So what do we see here? We have 3 resistors, 12, 4, and 6 ohms. 2 ohms, of course, is not part of the circuit, right? So these terminals are open. And the open terminals are where we are going to perform our analysis. We need to find VOC, the open circuit voltage between those terminals, A and B. And remember, our analysis assumes a polarity of plus up top and minus at the bottom. Does not really matter, but we have to keep track of it till the end. So what do we see in the circuit? 12 and 4, are they in series? No. How about 12 and 6 or 4 and 6? 12 and 6, parallel or series? It absolutely is in series. And the reason is, if you take a look at the circuit, we are simply measuring the voltage at A and B. But let's say, the 30-volt source is connected with plus up top, so the current is going in this direction, right? The current is going in that direction. When it reaches the top, it's going to flow in this direction. How about when it reaches the junction? Does any current flow through the 4 ohm resistor? No, because it's a dead end street. Current needs a pathway to flow through. If there is no connection, current cannot flow through. So all of the current is actually coming down the 6 ohm resistor. If there is no current flowing through the 4 ohm resistor, what is the voltage drop across that 4 ohm resistor? Exactly. There is no voltage being dropped across that resistor. So the concept here is, if you have a component like a resistor that is not connected at one end, it's left hanging in the air, then the voltage at either end of that resistor is exactly the same. V4 is 0 volts. The voltage measured across that 4 ohm resistor is 0 volts. Okay. And so point A has the same voltage as this node right here. And that's the important concept. If a resistor is not connected at one end, then both ends have the exact same electric potential because there is no current flowing, basically 0. And so the voltage at A is exactly the same as the voltage between 12 and 6 ohm resistor. We'll take a 10-second pause while you think over that concept. Let me know if you have any questions. Any questions? By the way, what was this talked about in physics? Physics 3, physics 2, physics 3 at all? I'm just curious. Okay, so we established that 12 and 6 are in series because it would be like the 4 ohm resistor is not connected. I will draw the circuit diagram in another way. This can be drawn like this. This is the 30-volt source. This is the 12 ohm resistor. This is the 6 ohm resistor. And this is the 4 ohm resistor. A and B. And for the purposes of analysis, that terminal also is kind of A and B. Same circuit, just drawn a little bit differently, that's all. So what technique comes to mind? Remember, once you're done with the problem setup, you can use any technique you want. Mesh current analysis, node voltage analysis, superposition, KVL, KCL, Ohm's law, resistors in series with the voltage. What happens to voltage when it's connected to a series connection of resistors? Yeah, it gets split or divided. You can apply voltage division, or you can apply Ohm's law, find the current flowing through the circuit, apply Ohm's law again to find the voltage across that 6 ohm resistor. I would choose to apply voltage division. And so I can say VOC, and let's draw this down here. VOC is a fraction of the 30 volt source. The fraction is given by 6 divided by 12 plus 6, which gives me 6 over 18, 1/3 of 30 is 10 volts. And VTH is VOC, so 10 volts. So my Thevenin voltage for this circuit is 10 volts. Again, the circuit, once you redraw it, could be very different. And so the analysis technique that you choose, it depends on the circuit and you, of course, right? Every individual can choose whatever they wish. In this case, we have one source, so we don't need to use any mesh current or node voltage analysis techniques. Just simply apply voltage division or Ohm's law, and you can find our answer. So VOC is Thevenin voltage. The Thevenin voltage in this case is 10 volts. Now, what do you predict the Norton current would be? This is 10 volts, and our Thevenin resistance is 8. What should our answer be? 10 divided by 8, 1.25 amps. However, if this is, and this is the second point why we need to find all three quantities independently. Let's say we get either RTH or VOC or VTH incorrect. So if you get one of these two incorrect, then the third quantity will also be incorrect if you apply Ohm's law directly. And that is another reason why we need to find the third quantity independently. Okay. So if there are no more questions for VOC, I'll move on to Norton current. Last call. Yes. Sure. So we established that the 4 ohm resistor has no effect on the circuit because current does not flow through it. And because current does not flow through it, the voltage at both ends of that resistor is exactly the same. So if you're trying to find the voltage between these terminals A and B, we can conclude that A has the exact same voltage at the other end of that resistor. And so what we're trying to do is, since we're trying to find this, we can find this because it's the same. So we're trying to find the voltage across the 6 ohm resistor. And to find the voltage across the 6 ohm resistor, we can apply, this is voltage division. But we can apply Ohm's law and find the current that is flowing through the circuit. This current I will be the same for 12 and 6 because of the series connection. Nothing is going down this pathway. Nothing is going through 4 ohms. All of the current supplied by the 30 volt source is going through 12 and it's also going through 6. So we can find the current I would be equal to 30 divided by 12 plus 6, right? And then we can find VOC by taking I times 6. Voltage division is just a shortcut by combining these two steps together. So one step. Does that make sense? Right? Okay. All right, Norton current. Let's move this a little bit to the side. Okay. Norton current. So for Norton current, again, we forget about all of this, right? That circuit has no bearing on the circuit for Norton current because the circuits are different. I have the 30-volt source. I have the resistors. In order to determine the current, I need to place a short between those terminals. Remember, current needs a pathway to flow through. So there has to be a short circuit. I'm going to call this ISC. ISC, of course, is my current. 30 volts, 12 ohms, 6 ohms, and 4 ohms. Different circuits, right? These two are not the same. These two are not the same. Keep that in mind. Thevenin voltage requires the terminals be open. Norton current requires that terminals be closed or short-circuited. So a tiny short at the terminals of analysis now renders the 4 ohm resistor in parallel with 6 ohms. Thevenin voltage analysis, the 4 ohms was not part of the circuit because of the open circuit. Now it is. And we can see that the 4 ohm resistor is in parallel with 6. I can redraw the circuit. And the circuit can look like this. This is the 12 ohm resistor. This is the 6 ohm. And this is the 4 ohm. And I need to find the current ISC. If you look at ISC and you extend the arrow, what do we see? ISC, the short circuit current between the terminals, is the current that is flowing through the 4 ohm resistor. Does everybody see that? ISC flowing between A and B is the current that is flowing through the 4 ohm resistor. So this is A, this is B. Again, every circuit is different, so the analysis is different. You as an engineer need to be able to determine which analysis technique to choose. Redraw the circuit as many times as you want until it starts making sense, okay? Take it step by step. Do not be in a rush. By the time the exam comes, you should be able to practice this enough. Okay, so let's mark out ISC would be the current flowing through here. This is the total current that's flowing through the circuit. I'm just going to call it I for now. .30 volt source. So we can analyze this multiple ways. Combination of applying Ohm's law 2 or 3 times, applying current division, find the total current I being supplied by the 30 volt source, or you can apply series parallel analysis. It's basically a combination of 2 or 3 different techniques, right? The easiest, of course, is to reduce everything down to one single resistance and find the total current I in the circuit, and then you can apply current division to find ISC. Or you can find voltage across the 6 and 4 ohm, which is again just a 2-step process of not applying current division. So if I was to reduce this to one single circuit, I would have the 12 ohm. This is a parallel combination of 6 and 4. I'll call this I. And I can write I is equal to 30 volts divided by 12, which is in series with a parallel combination of 6 and 4. Parallel combination of 6 and 4 is 6 times 4, 24, divided by 6 plus 4, which is 10, should give me 2.4. 12 plus 2.4. And total I should be 30 divided by 14.4. And that is, let's see, what is that? Remember, this is the total current in the circuit, not the ISC. .083. Okay, this is just the total current I being supplied by the 30 volt source. I could find the voltage directly. If I wanted to find the voltage, I simply apply voltage division, and I can do this. I can find the voltage across this parallel combination. I'll call it VZ. VZ. So this is total current I. If I find VZ, VZ can be given from voltage division, 30 times 6 parallel 4 divided by 12 plus 6 parallel 4. This is from voltage division. From here, I can say VZ is equal to I times 6 parallel 4. I'll leave you to do that calculation. Here, it would be 30 times 2.4 divided by 14.4. And this comes out to be 5 volts. It'll be the same thing here. I would be 2.0833 times 2.4. And that should come out to be into 2.45. Let's take a 10-second pause while you look over both methods. One on the left, simply a shortcut, voltage division application directly. One on the right, I'm applying Ohm's law to find the total current I being supplied by the 30-volt source. Then I find total current I as 2.083. At that point, I can apply current division because the total current I is splitting between 6 and 4. All right, think over this and let me know if you have any questions. The steps make not steps. Does the method make sense? Maybe, maybe not. As far as circuits go, this circuit is rather straightforward because it only has one source and a reducible network of resistors. Okay. From here, if I wanted to find ISC, ISC would simply be 5 divided by 4, 1.25 amps. Because VZ is a parallel combination of 6 and 4, voltage across the 6 ohm resistor is 5 volts. Voltage across the 4 ohm resistor is also 5 volts. So if I take it back here, VZ is here, and VZ is also here. Remember, they are in parallel. So once you find VZ, you apply Ohm's law, you find ISC. If I wanted to apply current division, I would apply it after this step. That's rainbow colored. So from current division, I can write ISC is I times REQ. Actually, let's not do it that way. I times 6 parallel 4 divided by 4. .0833 times 2.4 divided by 4. That still gives me 1.25 amps. Two different methods, the same answer. Does that make sense? You might have to review this right after class ends. Therefore, my Norton current is 1.25 amps. Verify your answers by applying Ohm's law. IN is 1.25, RTH is 8. That does give me 10 volts, which is what I found for VTH. I'll give myself a green tick. Job's not yet done. Remember, we are asked to find Vx. Well, we are asked to find Thevenin and Norton equivalent circuits for that original circuit. The follow-up question was determine Vx for a particular value of, of that resistor. In this case, the resistor was 2 ohms. We still have to finish drawing our final Thevenin and Norton circuits. So our final Thevenin circuit should look like this. Thevenin circuit should have a voltage source in series with a resistor. This voltage source is 10 volts. Remember, that is the Thevenin voltage we found. The Thevenin resistance was 8 ohms. And a resistor was connected here. The 2 ohm resistor. This is A, this is B, plus minus, and this was given as Vx in the original circuit diagram. I wanted to find Vx now for 2 ohms. Vx is 10 times 2 divided by 2 plus 8, 2 volts. So it was given as Vx in the original diagram. Our Norton circuit should look like this. Hold on. I'll draw it out here. Norton circuit should have the Norton current in parallel with that resistance. RTH, which was 8 ohms. And our 2 ohm resistor connected back into the circuit. A, B. So when I ask you for the Thevenin circuit and Norton circuit, this should be your final step, your final answer. Draw the Thevenin and Norton equivalent circuits. All right, we're going to end class here with this example. What I'm going to do is I will post a video showing the solution for the next circuit. Okay, so I will have that video up sometime, hopefully before my lab class ends today. If not, at least by tomorrow. Okay. If you have any questions, so I'm going to end class here today. If you have any questions, we still have a few minutes before the next section begins. Otherwise, I will see you all on Friday. Get started on the homework. Again, the homework due date I will post. So it's already posted as due on Friday, but I will push it back to like Sunday. And the quiz on Monday will be on Thevenin and Norton. Okay, so get started on the homework. Get in touch with me. I will be in my office tomorrow. I'll have open office all day long. So send me an email, stop by my office, meet on Zoom, anything is fine. All right.